can start it. Yeah, I was saying the first thing we're going to look at is the squeeze lemma. You guys might have seen this in Cal 1. Sometimes I think when I'm going through my course, I don't even mention it, but it's supposed to be in Cal 1 for limits of regular functions, but it also applies to sequences. So the squeeze lemma. So let's go through what it says. So let A subscript n, B subscript n, and X subscript n be sequences. So let A n, B n, and X n be sequences. Of course, you need the brackets to signify a sequence. So let A n, B n, and X n be sequences such that A subscript n is less than or equal to X subscript n, which is less than or equal to B subscript n for all n in n. For all natural numbers n. Full stop. So you should have let A n, B n, X n sequences be sequences such that X n is between, well, ranges from A n to B n for all n in n. Full stop. Suppose sequence an, suppose sequence an and sequence bn converge. And the limit as n tends to infinity of an is equal to the limit as n tends to infinity for bn. So suppose an and bn converge, and the limit of an as n tends to infinity is equal to the limit of bn as n tends to infinity. Then sequence xn converges and the limit as n tends to infinity of xn is equal to those two. Then sequence xn converges and the limit as n tends to infinity of xn is equal to those two limits. Be right back. All right, I'm back. So everyone has that?
Yes, sir.
All right, good.
Yes, sir.
Hold on. You know, let me show a quick example. I wasn't going to do it, but I was going to go through the different theorems, but let's try a quick example. Suppose we want to complete, sorry, we want to find the limit of, we want to see if a certain sequence converges. So I'm going to give it a sequence. 1 over n root n. All right. So we're using this. This is, of course, for all n in n. This is n is a natural number. All right. Now we know, so we want to check to see if this converges and also if we can find what it converges to. So if I told you to use a squeeze lemma, so the thing you wrote a while ago is called a squeeze lemma. If I told you to use a squeeze lemma to find the limit of this, or to find if it converges and what it converges to, you could consider two things. What number do we know that this sequence must be bigger than? Remember, n is a natural number. So what number must it always be bigger than?
0.
0, good. So far we know that 0 is less than or equal to this. Of course, we know it's not going to be equal, but it must be bigger than it.
So would we put an equal sign underneath it as well, or do we just remove it and put the greater than?
You can put equal, but since the squeeze lemma includes the equal, you can put it there. Because once it's a greater than or equal, the greater than takes care of the other part.
Oh,
Because when you want to apply the squeeze lemma, you should have the greater than or equal to. And once you know it's greater than it, you can always put equal. So you know, for example, that 5 is greater than or equal to 4. You have to put greater than, we can also put equal as well. It's still true.
you
All
sure
right.
that's correct, sir?
Repeat that?
You sure that statement there is correct?
Yeah, fine, very sure.
The equal sign?
Isn't 5 greater than or equal to 4?
I don't know about equal part. I'm just thinking it's greater than.
Listen carefully. Greater than or equal to 4. I didn't say greater than and equal, isn't it?
Okay.
Or.
Okay.
That's why when you have x is greater than or equal to 2, x can be 2 or more.
True.
So if x could have been the number 6, because 6 is greater than or equal to 2. Make sense?
Yeah.
Or are you still confused about it?
I'm
You get it? Okay.
a little confused, but
Really, Anthony? All right, we'll soon talk about that.
all right.
I don't want to spend too much time on it. But I'll show you later why it works. All right. What was I going to say a while ago? Oh, yes. On what sequence we know the limit of that it must be less than or equal to. This time the equal applies. We worked out a limit before of a sequence. Well, as a matter of fact, we did it many times, maybe 3 times.
If you remove the n, the outer n, I guess you probably can have it 1 over the square root of n.
Which one ends it talking?
I think well, yes, they remove the square root of n.
Right. Because we work with one of our n all the time. So, a matter of fact, when generally you're going to have some sequences that you we call them now. Generally is not the word. Common sequences. 1 over n is one of them. 1 over there's another 1 over something. No, 1 over n is a general one. Just like when you have the graphs, like y equal x is a common graph, y equal x squared. Those are what you call the basic graphs. You have some basic sequences as well. I need to list them. I don't remember them off the top of my head, but I'll list them to you so you can know when you need to pick. You're going to pick from those when you do the squeeze lemma. When you apply the squeeze lemma. So this is one of them. 1 over n. So 0 is always going to be less than or equal to 1 over n times root n. Of course, it's less than it all the time because n is a natural number. And even if n was not a natural number, 0, that thing can't be equal to 0. But we know it's always greater than 0. And it's always less than or equal to 1 over n. When is it equal to 1 over n?
When n is 1.
Correct. So when n is 1, the first natural number. After that, it's not equal anymore. It's always going to be less than. 2 root 2 is going to be less than 1 over. 1 over 2 root 2 is always going to be less than 1 over 2. 1 over 3 root 3 is always going to be less than 1 over 3, and so forth. But when it's 1, it's equal. Anyway, so we are confident that this is true. Anthony's a bit weary about the 0 equal, but let's use the greater than, then we are confident about the greater than part. Now, so all we have to show is, since this is true, we can check the limit of the left side and the limit of the right side. So what is the limit? as n tends to infinity of 0 equal to?
0.
0. When you guys paused a while ago, I'm starting to worry. All right, so what is the limit as n tends to infinity of 1 over n? That's what we know already. We actually prove it too.
0.
0 as well. So since both limits, left and right, are equal to 0, it means, remember, the limit of a sequence is what the sequence converges to. So both sequences have a limit of 0, which means that both of them converge to 0. Of course, the left one is not moving, it's a 0 from the beginning, but the right one is converging to 0. So since the left limit is converging to the 0 and the right limit is converging to 0, that means the middle one is also converging to 0. Therefore, the limit as n tends to infinity of 1 over n root n is equal to 0 by the squeeze lemma. So it's a simple application like that. The hardest part is finding the two sequences or two terms, because of course you can see the one on the left is just a number. We have to be able to figure it out. Normally when you have the rational expression, it's going to be 0. Normally, not always. Sometimes it's 1. Depends on what it is. You can figure out that it must be greater than that or equal to that. So anyway, any questions about that?
No, sir.
Okay, is it the one on the left? They call it a. I should tell you that to confuse you. Leave it alone. Of course, I can tell you. Sure. The one on the left. The this. What do you think this is called? Let me see if I can draw it properly. The sequence with 0. What do you think is a special name for that? Think of what the 0 is. Start with C. What kind of sequence is that? The 0 is a number. What's the next name for a number? In function. Let me give you an next clue. Start with CO.
Is it color? I can't remember the name. Culinary.
No, 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 no. You're talking about lemma and corollary and those stuff. No.
Okay. Oh.
All right. Let me give you a biggest hint I can give you now. Is that sequence changing as n changes? We're talking about this, you know. Is this sequence changing as n changes?
Wait, convergent.
Constant, sir. Constant.
Constant sequence. That's a name.
Oh, constant. Okay. Wow.
So when you see a sequence with a number in it, that's called a constant sequence. It's like if you have f of x equal to 0, f of x equal to 1, that's a constant function. So that's a constant sequence. And we won't be using that term, but that's I wasn't going to really mention it, but I might say it. So there we go. Anyway, next theorem.
So
Oh, sorry, go ahead.
if it's not a constant, we have variable sequence too, or no?
Well, just have sequence. Well, of course, if you want to give it a name, then it's a changing sequence. So I suppose it varies, but although you can see a perfect pattern taking place.
Oh, okay.
But a sequence that doesn't change value is a constant sequence. But I don't think I've ever heard any name used when it actually changes the sequence. All right. Next theorem. So I'm going to give you as much of them as possible and then do some examples. So there's an example of one already. All right. Next one is, this one doesn't have a special name. It's kind of straightforward, so maybe that's why there wasn't a name for it. It's a lemma used to prove a next theorem. So here's what it says. Let sequence xn and sequence yn be convergent sequences. Let sequence xn and sequence yn be convergent sequences. And sequence x, sorry, not sequence, and xn is less than or equal to yn for all n in n. That looks like 1 over n. This is yn. Yeah. For all n, for all natural numbers, n. Then the limit as n tends to infinity of xn, limit of y tends to infinity, beg your pardon, n tends to infinity of yn. What do you think should be between them? Here's a hint, it's easy. If this thing is always just not equal to this thing, then what do you think happens with the limit? Welcome, Michaela. Okay,
Sir,
take it
is
less
that
than or
sign
equal to it.
equal sign between them, or is it less than and equal to?
Less than or equal to. So then the limit of the xn is less than or equal to the limit of the yn, as n tends to infinity. But I told you guys it was easy, no? I think sometimes you think too hard. All right, next, we're going to look at, I think this is the one that, no, this is not the one I wanted to get to yet. Next, we're going to look at a proposition. So here's what this one says. So that one is finished. Let sequence xn be a convergent sequence. So let sequence xn be a convergent sequence by Michaela, such that x sub n is greater than or equal to 0. Referring, it looks like Michaela went for a walk. Oh, Michaela. So let sequence xn be a convergent sequence such that x sub n is greater than or equal to 0. Then the limit as n tends to infinity of the square root of x sub n is equal to the square root of the entire limit. That will be useful later. You see, if we were in class now, I'd be going through the proofs of these. So you could probably prove them back on the exam, but it makes no sense to go through that now. You just write it right back with your notebook. And we can't have that. Now that same thing applies for absolute value. I'm going to give you a proposition for that as well, and then get to the thing that I want to get to. Anyone still write? Well, no, I don't think you're writing this. So erase this. Next one. The final proposition before the one that I want to do some examples on. If sequence xn, you know, the same thing in brackets, is a convergent sequence, if sequence xn is a convergent sequence, then sequence absolute value of x sub n is convergent as well. Then sequence, that thing right there, sequence absolute value of xn is convergent. And the limit as n tends to infinity of the absolute value of sequence of xn, absolute value of xn, is equal to the absolute value of the limit as n tends to infinity of x sub n. Oops, whatever.
Sir,
Yes.
the math degree can get an harder than this, don't it? Than this course.
Well, I don't know. You see, what I did was this was I did topology as well. I think topology is either the same as this or a little bit more difficult because it's kind of abstract.
I don't
But
see that on that's not a part of the program. That course is really called.
no, man, no, you do that in masters.
What?
When you say master degree, you're talking about bachelor's?
Yes.
Oh, no. This is as you know why this is hard? Because generally in math, you can say, okay, you can use this for that, you can use this for that, you might use this in a certain course or whatever. You see them things, yeah?
Mm-hmm. It's not related to anything else.
Not that I can think of. It's just
Sir,
mathematicians showing that they can use math and fix up some more math stuff. That's what I think.
sir, I'm happy that you acknowledge that it's hard. Because I was wondering if it's just me, you know.
No, that's why it's hard because you can't see where you're going to apply it. And like you say, okay, now I'm going to show you something in calculus. You can say, all right, let's see an application of this in real world. And it starts to make sense. But there's them things, man, abstract stuff. That's why it's difficult, in my opinion. But that's why it's difficult to me, or was difficult. Topology, it has a lot of this stuff in topology. That's why I hated the course.
A lot of these stuff are in the other course just mentioned, in the master's program.
It's called topological spaces. I don't know. You see, when I did it though, I did it in bachelor's because I did it as an elective at UA. I did it because it fitted perfectly with my schedule. When I did it, man, I almost dropped the course, but then I stayed in there. This is the course. That's the course I was telling you about. I started with about 21 of us, I think it was. I remember exactly. 21, I remember.
Okay, I remember.
And in the end, it was 3 of us. And then one of us still failed. Or one of them, because I didn't fail.
Okay, sir.
I remember when I went to the teacher and I got a 70, I think I got 71% on the first test. And I went to him. The first test had 10 of us there, because most of them had withdrawn. And I got 71, and I said, sir, what was the highest in this test? He looked at the grades and looked back at me and said, you got the highest. I was like, what? But I have 71. He said, yes. That time I started fret. Because if I found the thing so difficult and I was getting the highest in the class, then my gosh, man. There were 2 master students in there. One of them withdrew, one of them stayed. And I beat the master students. So you see what rough the thing was? Because even though it was a elective, it's a course you have to do when you're doing the master. In math, straight math. But I would never do that course otherwise. You have to do it because you're going to do masters in math, but I did masters in actuarial science, I wouldn't have to do it.
So pray for me when the time comes.
You will get through, man. You see, because you do this already, it'll be a little easier when you do it. A little easier. But I didn't do this course at all. I went straight to that one. It was a bit harder for me.
Okay, sir.
No worries, man. Don't worry about it. You'll manage. All right, so we're going to look at some tests. Yeah, man, don't worry. Some tests for convergency. We're going to do 1, 2, 3. Yeah, these 3. But I'm going to focus more on one of them because that's the one I'm going to test you on the most. So the first one, we call it proposition. Call it what do we call it? Convergence test number 1. I don't like what I call it. Call it that so you can find it. It can be easy for you to find it when you're looking through your notes. Convergence test number 1. All right. Here's what it says. Let X sub n be a sequence.
So what you still calling it?
Convergence test number 1.
Okay.
The third one has a special name, but these don't. These two don't. And this is the first one. So convergence test number 1. Let X sub this thing right here, the thing up here. Let this sequence X sub n be a sequence. Full stop. If there is an X in R, if there is an X in R and a convergent sequence A sub n, write the word sequence this time now. So, sorry, if there is an X in R and a convergent sequence, sequence X sub sequence AN, such that the limit as n tends to infinity of A sub n is equal to 0.
Sir, could you go back to and a convergent sequence?
Then you write this.
AN, okay. Continue, sir.
Such that that limit A of AN is equal to 0. And the absolute value of X sub, oops, that looks so mark that. Absolute value of X sub n, yes, minus X, remember that X we mentioned before, is less than or equal to A sub n for all n, then sequence X sub n, so that means the special brackets, sequence X sub n converges and sequence X sub n converges, and the limit of sequence X sub n is equal to, let me give you a chance to get a little bonus mark. What do you think the limit is equal to? Based on information you've gotten. Read through it and see if you can tell me what the limit is. In 1 minute.
0.
Sir, 0.
No. I'm going to give you a hint when you have 10 seconds left.
Negative infinity.
No, man.
Only infinity I can think of X.
Ten seconds left. So wait,
AN.
Anthony said something a while ago.
Yes, sir. I said infinity.
Oh no, not that. So here's the hint. 10 seconds.
A, A,
10, no, 9, 8, 7, 6,
X.
5. Yeah, guess what everything you? Yes, X is correct. Why is X?
uh, well, I'm looking at the thing you underline,
Mm-hmm.
and I I'm assuming if a n goes to zero, then
Right.
you
Just
will
like if
type,
we're going to epsilon.
yeah.
Good, good, good. Because normally when you write this, the limit of a sequence, you're proving that the sequence minus L is less than epsilon. Epsilon is normally a small number. As you can see, a n is going towards zero. So it's a small number as well. So this would not be the limit. Some of these things are intuitive, or you can actually figure them out. Anyway, so that's the answer. So right, limit as xn. Remember, this is supposed to be n into infinity. If you don't see anything written down here, it's n 10 into infinity.
Always.
For sequences, yes.
Oh, okay. How much is the bonus?
You think the test was hard?
Yes, yes.
All right, 4 marks then. If it was easy, I get 2. All right, we can make it 5. No, 5, nothing, no, 4.
I tell me, I beg you
Math,
half of them marks left.
math
Uh,
342, Anthony,
yes.
4 marks. Okay. I have to make a note of these things because I forget them all the time. In my other
Remember me
courses.
and left. Remember me and left and get some early marks early up, sir.
You did?
Yes.
I don't see any record of that.
Yes, sir.
Maybe I didn't write it down. Let me write it down. So, did I tell you how much it was? No, but I can't tell me the line now.
Lafern, do you remember?
I think I've only been given 3, so let me put a 3. Oh, both of you had split something? Like I had split the marks
No,
about a question?
no. It's two different something. Two different
Or
things.
2 different questions?
Yeah. If I ever go to the
All
recording.
right. Let me give reference 4 and give you 3. So you're gone 7. Can't give it too much, you know. All right. Oh, already know that. Oh, that. Next proposition, next test. Convergence test number 2. So this one, if you have a special x in, well, come back to it later. Let me show you the examples you see it. Convergence test number 2. Here's what it says. Let C be greater than 0. Full stop. So all we've assumed so far, that C is a number and it's bigger than 0. So it's positive. Number 1, if C is less than 1, then, so if C is less than 1, remember it's positive, you know. So it's a fraction between 0 and 1. So if C is less than 1, then the limit as n tends to infinity of C to the n, use a brain again. What do you think this is equal to? Remember, it's a sequence. So you're checking what this number is going towards.
0.
0. Because the denominator is always going to be bigger. So when you raise to a certain power, the bigger the power, the bigger the denominator gets in comparison to the numerator. For example, 4 or 5. Even though 4 is so close to 5, as it gets bigger and bigger and bigger and bigger and bigger, the 5 raised to the whatever is increasing a lot faster than the 4 raised to the same power.
Yeah. I was
So
thinking
it's
of
tending
it.
towards 0.
I was thinking it from the sense. I was thinking of it from the sense of the power being negative. So you would write that as 1 over whatever number. 1 over C. whatever power it is.
Which power be negative?
Well,
The n?
oh goodness. No.
So it's like a book up to get the 0 a while ago. At least you got it though.
Yeah. I was thinking that it was the
Okay.
end that one. So you basically wrote it as 1 over C2.
Oh, the c. Remember the c was actually a fraction already, you know.
The C was actually a
So
fraction.
maybe that's why you were thinking about that. C is a fraction because remember we said that c is positive and it's less than 1, so it has to be a fraction.
That's true. Yeah, that's true.
Sorry. Yeah, so it ranges from 0.0000 million zeros and then 1 up to 0.9999999. Yeah. So next one. If c is greater than 1 now, then oh, that looks so weird. That's supposed to be a c, okay? C greater than 1. It actually looks like less than greater than. So if c is greater than 1, then what do you think is going to happen with this sequence here? If c is greater than 1, what do you think is going to happen? Think about the limit of that sequence.
Sir, it tends to infinity.
Right, and what's the word for that?
Increases.
No, I mean, if it's not converging, it is.
Divergent.
Right. So then the C sequence, that sequence right here, diverges, or you can write, is unbounded. Because as Lafferent says, it's going towards infinity, so it's not bounded at all. So when something is not bounded, it doesn't converge. When it doesn't converge, it's not bounded. Both of them are the same thing. Well, I shouldn't say that, you know. That's not true. You can be bounded but not converge. Shouldn't be spelling for the doctrine. Alright, matter of fact, I showed you a sequence like that before. This one here. That doesn't converge, but it's not unbounded.
What's the tab in there, sir? Or negative 1 to the n?
Negative, yeah.
Just alternating.
But it's bounded though. Bounded by negative 1 and 1, but it's not converging.
Bounded by the
So it's
two.
possible. Huh? What's that?
And so it's bounded by the figures that it's alternating between.
Yeah. So it's possible to be bounded and not converge, but it's not possible to converge and not be bounded. I think I mentioned that before. Now for the convergence test number 3, this one now has a special name. This is what I'm going to focusing on because I like questions on this one. Like the ones before, you have to sometimes figure out stuff to use and pick up this and whatever, but this one, straightforward. Well, I shouldn't say straightforward, it's more intuitive than the others. So this one is called, you can call it convergence test number 3, but the special name is ratio test for sequences. The ratio test for sequences. Oh. So I'll soon show examples for those two. Ratio test for sequences now. This one is the third and final test. Let x sub n, or let sequence x sub n be a sequence. When I say sequence x sub n, I mean put the brackets. If I don't say sequence, I don't have to put the brackets, or I shouldn't. So let sequence x sub n be a sequence such that x sub n is not equal to 0. Such that x sub n is not equal to 0 for all n. and such that the limit L and such that the limit L, sorry, is equal to the limit as n tends to infinity x sub n plus 1 over absolute value of x sub n, and such that the limit L equal that exists. So the test that we're going to talk about now depends on that limit. So you see why x sub n could not be equal to 0, because we're going to be dividing by it. So I have to let it be a sequence such that that limit right there exists. Number one. So here's what ratio test says. If that limit L is less than 1, then the sequence x sub n converges. Now finish it, you know. I wonder if you can squeeze it. Yeah, I can squeeze it in here. If the limit L is less than 1, then sequence x sub n converges, and the limit of the sequence, here's what is interesting, is equal to 0. A pretty proof for it, but pretty long too. So I'm not gonna go through that. Even if I was asking me to remember the proofs and prove them back in the exam, I wouldn't ask to prove this one. One of the longest proofs I've seen. But it actually makes sense. And two, if L is greater than 1, then sequence x sub n is unbounded. Or you can put diverges as well. So, you know, that's diverges. I was trying to squeeze, put it down here. Diverges. Oops, I forgot how to turn on my phone. All right, so everyone has that? Example time. I won't tell you which one it is. Let me just give you an easy one to see if you can figure it out. Let's try this one. What do you think is the limit as n tends to infinity of 4 to the third power over 5 to the n power? What do you think is the limit for that?
I would say infinity.
All right, so if you say infinity, what would you conclude about this sequence here?
Diverges.
All right. Before I ask you why, let me give you a different one. What about that?
That one is weird. I would say that one goes out to 0.
That one Come again? Say that again. That one what?
Converges.
Converges
Yes.
to what?
To 0.
Alright, so since you said this one converges, since you answered for both of them, why do you think the first one diverges?
Well, because the the limit as n tends to infinity of the numerator, which would be 64 to the n power, it moved faster than the one below, which is 5 to the n power. So
Alright.
because the one at the top moves much faster than the one at the top, it basically will go up to infinity.
Alright, that makes sense. Why is it why is the next one converges and why is it equal to 0?
Because, well, 5, what do you call it again? Oh goodness. What's the 5? What does exclamation mark mean again? I forget the name.
Factorial.
Thanks. Because you have 5 factorial, that would actually be 5 times 4 times 3 times 2 times 1. And if you're going to, well, if you had the power outside, that each of them would actually be, well, each of those factors, you have 5 to the n times, well, I'm some thinking about it, 5 to the n times 4 to the n times 3 to the n times 2 to the n times 1 to the n. Now that 3 to the n in the denominator will cancel the 3 to the n in the numerator. So what you'll end up having is 1 over the 5.
Or whatever number is left to the n.
Yes. So because you have 1 on top now, and the end approaches infinity, you basically have a very big number underneath, and 1 will be on top. So basically, you'd end up approach. Well, yeah, it's similar to 1 over n. You basically converges to 0.
I was gonna ask you a while ago how you would prove it, but since you just mentioned that 1 over n a while ago. Wait, by the way, let me just ask you, how would you prove both of them? Prove no, I mean, you don't have to go through any long thing either. What would you do to prove that it's true? What you say is true?
What? What do you mean? How would I prove it using proofs?
There's an easier way. Remember, we just did something a while ago.
Oh, we can use the squeeze.
Saying something easier than that. It's one of the tests I just gave you.
Oh, the ratio test.
Yeah. Which one? No, not ratio test. Probably could use a ratio test, yes, but there's even one easier than that.
Convergence test.
Yeah, which are the convergence tests?
It's
not just you, Anthony, because I know the rest of them quiet. You guys too. Asking you, what would you use?
Good.
He answered. He gave the answer. Now you can tell me why, or what would you prove it with? Look at. It's not the ratio test. It's one of the other two. Which two? Which of the two?
My internet went when you were given convergence test. So get transferred on.
I'm actually giving the example. No, that's what these are the examples. All right, they might take too long. You see what you mentioned a while ago about the. Let's deal with the bottom one first. This is the same as limit. Matter of fact, the thing inside the bracket, you don't realize it's a number?
Yes, sir.
Inside both brackets, there's numbers. So you can call it a C, it's a constant. Actually, this bracket here, you mentioned that 3 cancels the 3, so we're actually 1 over 40. Because 5 factorial is 120.
Oh, okay.
So 3 into 120, you get 40. Or you could do 5 times 4 times 2, which is 40. So it's 1 over 40, which is actually less than 1, but greater than 0. Not true?
Yes, sir.
So it's convergence test number 2, part 1. This is a C. C is 1 over 40, which is less than 1, and at the same time greater than 0. So the limit of that is going to be equal to 0 as n tends to infinity.
How do you say less than 1 but greater than 0?
Less than 1 but greater than 0? What do you mean how you say it? Between 1 and 0.
I mean,
if a number is greater than 0, at the same time the number is less than 1, Between 1 and 0. Or
Okay.
between 0 and 1.
Right, okay.
Is what you mean by how you say it?
It's greater than 0 but less than 1.
Uh-huh.
Right. But I think you were saying less than 0 but greater than 1.
Really? Oh, sorry, mistake.
Okay. Okay.
So let me say it the other way. It's positive but less than 1. Right. So one thing positive noise must be greater than 0. So the limit of that would be equal to 0 based on ratio test number 2. So that's how you could prove it without actually doing any fancy proof. You could use a squeeze theorem as well, because the same thing that you mentioned about the that this here has to be less than 1 over n, because you're going to get 1 over 40. And n was already starting from 1, then 2, then 3, so it's just not equal to it. All right,
But sir,
where was I now?
also thinking about it, 1 to the n is really 1, really.
Mm-hmm.
And then you'd have 48 to the n as well. So that number
48
below.
to the 1?
Yeah, 48, 40 is 40 that? 40 to the n.
Yeah, 40, 40.
40
That's
to
0.
40 to the n power. So as n approaches infinity, it will ensure that the 1 over 40 to the n becomes 0.
Yeah, because the 40 will be 40 to the n is 10 into infinity.
Yeah. Yes, right. So it's like 1 over infinity.
Right.
Right, but still, but that is a much, much easier way.
Yeah, man, that's why. Remember, if I'm going to give you some topics and then give you some questions, it's going to be based on topics that we just did.
Yeah.
All right. The one I really want to get to do is a ratio test. This one is nice. This one you'll most likely see in your next test. So let me give you an example. Let's say we want to prove that the limit of as n tends, so you're going to use the ratio test to prove that 2 to the n over n factorial, right, that again, limit as n tends to infinity, 2 to the n over n factorial is equal to 0. So I'm going to prove that it is equal to 0 using the ratio test. So the ratio test says that if the limit as n tends to infinity of absolute value xn plus 1 over xn, absolute value xn, is equal to L and L is less than 1, then that limit is going to be equal to 0. So what we have to do is check what the limit of x sub n plus 1 over x sub n is equal to. Absolute value, of course. So let me do that right now. Remember, we want it to be equal to a certain value. And we want the value to be less than 1. If that is the case, then it converges and it's equal to 0.
Okay, question, sir.
So
Could
this is
you,
your x sub n.
could you explain
Yeah, go ahead.
the first part we have there? Are you saying that the limit of the function as n approaches infinity is equal to 0?
Yeah, we're going to prove that. That's what we're proving.
Oh, so we
So the
have to
question is, prove
prove
that that limit is equal to 0.
Okay, all right.
I think I probably wasn't so clear on that.
No,
So
man.
what we're doing right now is proving that this limit, this one right here, is equal to 0.
Okay.
That's our goal. So use the ratio test to prove that that limit is equal to 0. That's the question. Clear now?
Yes, sir.
All right. So what we're going to do is say limit. I'm actually going to write it down again. Make sure you know how we got to that result. So remember, our x sub n is let's squeeze it right here, right here, right here. X sub n is equal to that. I think that's a circle right here. So we're going to check what the limit of this over this comes out to be. So that will be the limit as n tends to infinity. N tends to infinity. That's infinity. X sub n. So that is 2 to the n plus 1 over n plus 1 factorial all over, so you can put absolute value if you want. You don't have to because it's a positive result since n is a natural number, but put it for the first part at least. Over 2 to the n over n factorial. Remember that is n plus 1 over n. So let's simplify this. Matter of fact, I won't even simplify. I'm going to go very slowly so you can see what is happening. Put the like terms together.
Question, sir.
Yeah.
The x sub n plus 1, the plus 1 is a subscript as well? Or is it?
Yes, sorry. I kind of wrote it bad. It's x subscript n plus 1.
Okay.
The n plus 1, both the n and the 1 are in the subscript.
Okay, good.
Yeah, the way I wrote it looked like x to the n plus 1. Are you right,
Oh, that's fine. That's not, I wasn't really understanding why we had the 1 in the power originally.
Yeah, sorry about that. All right, where was I now? Oh, so let's simplify this. So this is going to be 2 to the power n plus 1 over 2 to the n times, I'm splitting it so it's easier for you to understand, n factorial over n plus 1 factorial. Now it's your time. Simplify that for me, please. What's the fraction that we're left with? Or what rational expression are we left with? It's going to be something over something. What are the somethings? It's the algebra.
Sir, would it be 2n over n plus 1?
You are close, very close. What do you say,
2
Jeremy?
to the n over n plus 1.
No, that's what I say close. Wasn't that what you said before?
We have over to the right hand limit as n tends to infinity. 2n plus 1, 2n times n factorial over n plus 1 factorial. So shouldn't it have been 2n plus 1 over n plus factorial, n plus 1 factorial times n factorial over 2n?
Yeah, I just put them together so you can calculate it easier.
Yes, sir, but
so what you're saying is the same thing I have here now?
Sir.
Well, I just said it you have there?
Yeah. You said 2n plus 1 over n plus 1 factorial times n factorial over 2n.
Oh, yes, you move them around.
Yeah,
okay,
yeah.
just
Let's
see
put the
now.
like terms together. Yeah.
Sir,
Yes, Lauren?
is it 2 over n plus 1?
Yes.
There you go.
That is
When you said to the n, that's where we're going wrong. That's why I say we're very close. So when you divide 2n, 2 to the nth power into 2 to the n plus 1, you just have a 2. So you're going back to 2 to the 1. And what is the limit of that thing as n tends to infinity, people?
0.
0. You can actually do it the way that you learn in calculus if you want to be specific. Do it like this. Limit n tend to infinity. You can divide top and bottom by n. Over this one. Or you can actually realize that this one is going to infinity right away. Because the bottom part is going to infinity.
That makes it more complicated.
I'll just do it the calculus way. I think when you get, if you had done it right here, underline it. If you done up to here and you say equal to 0 because you don't have to even say anything. Because that's obvious.
Next to infinity.
Because it's 2 over infinity. So.
Yeah, because infinity plus 1 is infinity.
Right. Wait, am I writing this? What's that? This will be 0 over 1 plus 0. Yeah, which is 0. It's actually the same as 2 over infinity, just 0 from the beginning. Because the plus 1 is irrelevant. Anyway, I'll just do it in the calculus way, but it's the same thing. So if you could have written equal to 0 from right here, I wouldn't take off any math. So any questions about that? Everybody understand it? As I tell you, I made sure to spend time on this one because it's the type you get in the test. Yeah.
Sir, how did you end up with the n plus 1 at the bottom there?
N plus 1 at the bottom. Oh.
2 over n plus 1.
All right. Tell you what. Write this off first and then I'll show it to you. Because I need space to show it to you. So when you finish writing, let me know. And I'll show you why it's equal to n plus 1.
I think it's the factorial part of it where you have n plus 1 factorial.
Yeah, that's what I'm
Be
gonna
like
show you.
plus 1 times
I'm gonna
n.
break it down so you can see it. Be right back.
Oh, let's see. That would be n plus 1 times n factorial. That's how you did it, Luffy?
Said?
I was asking if that's how you did the bottom part, where you have n plus 1 all factorial. You expand it as n plus 1.
All right, I'm back. So you can let me know when you finish, Jeremy.
Yeah, I'm through, sir.
You finish? Okay. All right. So you're asking why is it n plus 1? So it comes from this part right here. The n plus 1 in the denominator. So it's the n factorial over the n plus 1 factorial. Now, n factorial means 1 times 2 times 3 times whole heap of dots, up to, let's say I have n minus 2. Remember, it goes right up to n minus 1, and then n. Whereas n plus 1 factorial, you multiply right up to n plus 1. 1 times 2 times 3 times n minus 2, n minus 1, n, and then n plus 1. You agree with those? You understand those, I should say?
N factorial, yes, sir. I agree with the top. The bottom,
How about the bottom?
n plus 1 factorial means n plus 1 times I don't see the bottom.
All right, let's say you have a number. Let's say 5 factorial, right? 5 factorial is going to be 1 times 2 times 3 times 4 times 5. 6 factorial is going to be 1 times 2 times 3 times 4 times 5 plus 1, which is 6. Agree with that?
Yes, sir.
N plus 1 is just like the 6 and the 5, where 5 is the n and 6 is the n plus 1. There's one extra number bigger than the 5. Let me show you 10.
Okay.
You sure you're
sir.
not being confused by the n minus 2 and n minus 1? You okay with those?
I'm not clear with the n minus 2, n minus 1.
All right. Those are just the numbers that come before n. Like say, let's say n was 10. If you're using what I had up here, it would be 1 times 2 times 3 times times 10 minus 2 times 10 minus 1, back foot, minus 1, and then, oh, this looks ugly, man, and then 10. How do I get that? What's 10 minus 2? 8. What's 10 minus 1? 9. Those are the numbers that come before 10. There's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. The 10 minus 2 is 2 numbers before the 10.
I understand.
10 minus 1 is in the number. Okay, right. So you see those numbers here, the n minus 2, the n minus 1, those represent numbers that come right before n. Now the n plus 1 is the extra number. Because remember, when you're doing a factorial, you multiply from 1 right up to that number. So if it's n plus 1, whatever the number is, if n plus 1 could be 12, you multiply right up to 12. It's just that n plus 1 is 1 more than n. You follow that?
Yes, sir. Yes, sir.
All right. Good.
Sir,
So, yeah.
very clear. I never thought of it this way, because I realize what you're doing is actually multiplying, starting from 1, right? And then go successively to the number itself.
Right.
But I usually start from the number itself, like say 5 factorial, start from 5, then
And go down.
Yeah.
Yeah, you could do that as well.
But the
I
way
was
in
going
which
to do that. If you didn't get this, I was going to do it that way.
but the way in which you expand it there makes sense to write it like that. But how I was thinking about it was like you have n factorial on top, and then at the bottom you have like n plus 1 collectively
Times n
times
factorial.
n factorial, and then cancel out the factorials.
Correct. I was just going to show him that I was just going to show so you know that this part right here, all of this right here is n factorial. You realize that, Jermaine?
Oh, yeah, that's going to be close.
Yes, sir.
So everything down there, apart from n plus 1, we cancel everything at the top. So all of this cancel, get 1. All that cancel, get 1. So let's say if it's 1 over n plus 1. It's when you're doing actuarial science courses, Jermaine, they're going to, if you go far enough in the P course, the math problem, math stats, you're going to see a lot of this. But they normally, to avoid writing all the 1 and the 2 and the 3 and whatever, they normally write it backwards. That's why Anthony thinks something like that. They normally write n factorial starting from n, then n plus 1, minus 1, beg your pardon. They normally go backwards. But it's the same concept.
I learned it backwards too.
Oh, then the same thing, man. You write it forward back,
I
the
learned
same
5
multiplication.
factorial is 5 times 4 times 3 times 2 times 1.
Yeah, okay. When you're doing, if you actually start to use this function called gamma, I think it's a gamma function, what looks like this. You're gonna learn some rough things about that. That's if you do the third exam in actual science. I don't know if they use it anywhere else, because that's the only place I see it. Maybe in some of the math courses you might learn it. In the master's course. Anyway, that's how I got n plus 1. Let me do the next example quickly in the 8 minutes we have left. You're saying something?
No, sir. Okay.
Oh, I thought someone said. All right, so let's do. I saw the next one and that was nice. Here it is. Oops. No, I didn't ask for writing. I hope not. So we're going to show the same thing for this. Show that the limit as n tends to infinity of n squared over 2 to the n is equal to 0. So this time I'm going to ask for the input. So let me start it off. Limit as n tends to infinity. Now you see the problem you might have in the exam is if I don't say that using the ratio test, you might go try to do it a different way and take long. So I think I might write using the ratio test to make your life easier. Because you might go try to prove it using the other thing. What the thing name again? Find the m and the epsilon rule. No, I think I can do it this way. If I say show, you know it's a ratio test or some other convergence test. And if I say prove, you use the epsilon business. Make sense? You guys hearing me?
Repeat again, sir.
Yes, sir.
I'm saying if I give you a test or exam question and it says prove that this limit is equal to whatever, then you know you're going to have to use the epsilon and this thing here, a n minus l less than epsilon. That's something to write it? I think so.
Oh,
yeah. Yeah, if I say prove, you use that. If I say show, you can use one of the ratio tests. I mean, one of the convergence tests.
Okay.
That's my advice to you. Because I would write show or write prove. This one is show. Here's ratio test. Anyway, so we're going to have to use limit as x plus, let me write it properly this time, subscript 1 down here. Good. Over xn. I won't bother to ask you what I should write here. Write it down. So this is n plus 1 squared. Replace the n's with n plus 1 over 2 to the n plus 1 divided by the same thing I had before, n squared over 2 to the n. I'm even going to go one step further. No, I shouldn't, you know. I am do it. Infinity. Because time is going, only 5 minutes left. So n plus 1 squared, I'm right the way Jermaine said it last time, over 2 to the n plus 1 times. I'm hearing an earthquake, you know. You can hear earthquake, I can feel it. Yeah, I hear it. There's something outside rumbling. Anyway, what next? What's that equal to?
N plus 1 squared on top divided by then you got n squared below for sure, but I'm not sure if you put that first. But you're gonna have 2 times n squared.
All right, that is correct. What next? You definitely use the calculus stuff now.
You can expand if you want.
No, if you want, you have to. This time you have to use the calculus method.
So you can expand the numerator.
All right.
2n plus 1 over 2n squared.
And let's cancel the n squared.
And you can divide by n squared throughout bottom and bottom.
Sure. I was hoping you said yes, And I would say, Anthony, what are you talking about? All right, so cancel n squared. All right, look here. I'm gonna divide numerator and denominator by x squared. Now I can't bother with writing, so I'm just gonna tell you what I'm doing. I'm gonna divide the numerator by n squared, divide the denominator by n squared. So I'm gonna get 1.
I was thinking, yeah.
I know. I just tell you that I'm not gonna write it. So I'm telling you what I'm doing. Okay. You told me, but I just making sure you know what I'm doing. So because I'm not gonna write it.
Okay.
Because I don't have the space. I don't have space, so I can't bother.
Do a half.
Do
a half equal to half.
Oh, you mean the answer, yeah. So when you put in the zeros, put in the infinity, you're gonna get 1 plus. Remember, the rule is the limit of a number over infinity. Sorry, what am I saying a while ago? The limit of a number over x as x tends to infinity is 0. So it's not that 2 over infinity is equal to 0, no. Never say that. Because I've seen students, no matter what, I'm going to finish what I'm doing and then I'll say it to you. So that one is 0, that one is 0, even more 0, if you can say such a thing, over 2. So it's equal to a half. But that's not equal to 0. Oh, what am I talking? What next? I almost start foolishness now. What next? Are we finished?
You're supposed to show that it's equal to 0.
Right. But we're getting half, so what is that then?
Contradiction.
No.
Laverne.
Sir, I'm gonna just say it can't be.
Between 0 and 1.
Hold on, Jeremy. Don't say anything. Wait, say what I'm going
Sir, I would just say that it cannot be proven.
Okay. All right. Jeremy, go ahead now. The reason I stopped to Jeremy because you were saying the right thing.
I was saying that the fact
what first. Go ahead.
That is half, sir. It lies between 0 and 1.
It's lies between 1?
0 and 1, he said.
Half is between
0 and 1.
0 and 1.
That's not the important thing, Leave off the 0. Say it again. Leave off the 0. And say it again.
Less than 1.
It has nothing to do with 0. Less than 1, correct. This is what was calculated a while ago. This is the L. Lafren and Anthony forgot about that. That is L. Look back at the ratio test. You have shown that L exists and it is less than 1. Half is less than 1, as Jeremy said.
What's up?
And based on the ratio test, that means that what? It means that the thing that we just looked at, this sequence here, converges and is equal to 0.
Sir.
You forgot about that.
Wait.
Go ahead.
So you're saying that what you said just show that I'm thinking about the normal limits when you have a limit converges.
No, you're mixing up what happened a while ago. We didn't calculate this limit a while ago. You see the thing online a while ago? That's not what was calculated. We calculated this one.
Oh.
Right. That's why you're confused. You missed Lafren as well.
Yeah, I think that's what both of us had the same thinking in our mind. So it's not.
You get it now, Lafren?
We weren't showing what we did a while ago is not showing that.
Sir.
Right. We didn't calculate that limit a while ago. We showed that the xn plus 1 over x is equal to a half, which is less than 1, which means that original limit
must
converges and is equal to 0. Right.
must convert to 0. Okay, fine, I understand it now.
Yeah, man. It was a trick thing. That's why I kind of a while ago. That's why I kind of say, but it's equal to half, not zero. I was kind of tricking you. So,
Yeah, but I think it actually
don't feel bad.
it really
Hmm?
helped us to understand
Right, I make sure you remember too when you do it in test. Because you
concept.
might have
Yeah,
done it in test and get the half and go fast and say, oh, but it's not right. And you probably write the wrong thing. So notice it happened to you one time. It happened to me before. That's why I thought it might happen to you guys too.
yeah.
I remember, as a matter of fact, it's when it happened to me for half an hour. I started working with the limit over and over again, saying, no, but I'm not getting zero, I'm not getting zero. Then I realized that, oh, geez, not applying the ratio test properly.
It's a conceptual error.
Right. So
Not
therefore,
understand.
this thing is equal to zero. Okay,
I like
that's it.
So, sir, can you give us
So
a couple to try for homework or something?
I will have a look if I have any more.
Sir, when is the last class?
Exam start December 16, I think, as well.
Or 15?
Yes.
The week before, whatever that
Okay.
date is. But we're not doing bad because I think we just have like two stuff left, and I say you see what I normally do with these courses is look for what you must get, and then whatever extra can be given if time allows. So far, we're almost to the end of what you must get in your notes. I'm not finding the questions here.
Can we get at least 2 more tests, sir? At most, 2 more tests.
Two more?
And yeah, we only did one.
Yeah, do.
Because
Anthony,
it's
a
hard.
madman?
Sir, it's hard, so we just choose the best 2. I'm sure Jeremy will agree with
Oh,
that.
that you want?
Yeah.
Oh,
It's,
okay,
You
that
heard,
makes
you
sense.
heard. Hey, you see,
Stand
once you
over
hear that
pressure.
girl laughing, you know, because I heard her laughing a while ago. Oh boy.
actually, all agree.
Sir, how you?
I know,
Laferd,
but I just know you. I was going to that. I just hear your voice in my head laughing.
Laferd,
Oh boy.
Yes.
you agree, ain't it?
Well, based on the first one, we're going to need something to make up, yes.
I
The
tell you
bonus,
what, I'll look for someone put them online because I'm
the
not
bonus
finding any right now
marks,
in the
the
questions.
bonus marks can help, huh? Where is it, sir?
I'm going to look for someone post it. The what do you call it?
Example, practice,
Yeah,
practice,
the
practice.
exercises online. No, no example exercise. You say you want them to try.
Oh yeah, 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 yeah.
I put them online after 2 because I'm not finding them right now. So when I get the break, I'll find them because I have to go
Oh,
to German's class.
okay, no problem.
All right. So this is good for them. Jeremy, you can remind me after Monday in algebra if you remember.
Yeah. So we
Okay,
get
sir.
into we get into more tests
All
there.
right.
No,
I'll
not
think
negotiable.
about it.
All
If
right.
it's 2 more, then of course one of them would have to be like the first one too, because apparently
Yeah,
you're not liking the grade for that.
yeah, yeah, definitely.
Just 3 of you, so people can do it. So I'll let
Yeah,
you
man.
know.
Yeah.
All right. So see you guys
Killer.
Monday. Wait, anyone? I don't even know if Michaela did the test now, but anyway, I'll check.
Okay, you said it's 3 of us, but